It's a useful introduction to this lecture because we are going to be dealing with errors in this lecture, and it is going to be one of these more mathematical lectures. We have to do a lot of linear algebra, and but the good thing is that we are going to be doing this with extremely simple equations. Okay, so we can really let's first of all review what we did at the end of the last lecture, and observe why the scheme we derived in the last lecture doesn't work, and we'll dive very deep into why it doesn't work. Okay, so just to remind you what we did at the end of the last lecture is we tried to obtain better ways to approximate du dt. So we're trying to approximate du dt instead of as a linear combination of two numbers, two time steps. We're trying to use a linear combination of 4 time steps, right? Remember, in forward order, we use the 2 time steps, we get a first order scheme. In midpoint is actually the best scheme that uses 3 numbers. So t plus delta t, t minus delta t, and ut. Although the coefficient on ut turns out to be 0. But even if we add a coefficient, we will have a 0 coefficient. That will be the best. So that's a second order scheme. If we want a third order scheme, we need to have a C1 times u at t plus delta t. So that's 1 point plus C2 times u at t plus C3 times u at t minus delta t, and C4. So a linear combination of 4 terms, t minus 2 delta t. Okay, so the question becomes, in order to get the most accurate scheme, what should be C1, C2, C3, and C4, right? And the right way to do this is Taylor series expansion. So we are going to be writing u at t plus delta t to be u at t. So I'm going to just shorthand, don't write the parenthesis t, right? Plus u prime. U prime is the first order derivative, shorthand, times delta t, plus half of u double prime delta t square plus sixth of u triple prime delta t to the cube, plus etc. So I have more terms that will turn out to be the error terms. If I want to get exactly what the error is, I need to write down more terms, right? But here, if I want to know, I want to get something that is better than second order, which means I want to cancel this term. I don't yet care about what error I get. I will just have this much of expansion. So that's the first term. The second term, u of t, would be equal to u plus 0 plus 0 plus 0, right? I mean, it's simply just the u itself. U of t minus delta t. The Taylor series expansion is u minus u prime delta t, right? Because it's at the minus point. Now plus half of u double prime delta t square. It's a plus because delta t minus delta t square is going to be plus delta t square. So the third order term is going to be minus again delta t cubed. Okay. And the last term is the one that takes a little bit of more calculation, but it's still pretty easy. So I have minus 2 u prime delta t, and I have plus 2. So because delta t square, 2 delta t square equal to 4. So it cancels with part of the half, and you get 2. And last, you have 8 coming out of the 2 cubed, right? So we have 4 over 3 u triple prime delta t cubed. And we have stuff afterwards. Now, in order to figure out what C1, C2, C3, C4 is, we are going to be writing things in a matrix form. Okay, we are going to be saying I want du bigger dt is actually going to be equal to a combination of several things. It's going to be equal to I'm going to write down the entire thing as a matrix, right? Okay, just to be very clear, so this matrix is going to be multiplied with these coefficients and added together, right? Not only the columns are going to be added together, the rows are also going to be added together, right? And the rows are actually multiplied by u prime delta t, u double prime delta t, and u triple prime delta t cubed. So when you multiply every row by a different number and add them together, what does that, how do you represent that in matrix algebra? We know that if I want to multiply every column by a different number and then add the columns together, that's equivalent to the matrix right multiplied by a vector containing all the coefficients, right? What if I want to add up all the rows of a matrix, each multiplied by a different number? Well, one thing you need to be pretty good at in actually most of the fields of engineering is that most of the fields involves linear algebra, and you really want to be able to represent a concept in linear algebra forms, right? In this case, it's actually if I want to add the different rows of a matrix together, right, each multiplied by a different thing, it's a left multiplied by a vector. So here I am going to just write down the matrix, and you can do some algebra in your mind to figure out that's the case. The matrix is going to be 1, 1, 1, 1. So that represent these 4 u's. And this row is going to be multiplied with a number u, right? And these 4 numbers is going to be multiplied by C1, C2, C3, and C4. Let me just use this to write it down. C1, C2, C3, and C4. Okay, so you can see that it's basically C1 times u plus C2 times u plus C3 times u plus C4 times u, right? And then we have the next, that is 1, 0, minus 1, and minus 2. This is multiplied by the second term in the row vector u prime delta t, right? Okay, and the third row of the matrix is half, 0, half, and 2. That's going to be multiplied by, I think let me write this a little bit more compactly, u prime delta t, and the third is going to be u double prime delta t square, and the last one is going to be u triple prime delta t cubed. Okay, and the coefficient is going to be a sixth, 0, minus a sixth, and minus 3/4. This is a really nice and useful way of writing down the linear combination of the Taylor series. Okay, every different derivative corresponds to each row of the matrix, and every different coefficient, unknown coefficient, corresponds to a column of the matrix. It allows me to really match the terms and solve for the coefficients. Okay, right? So essentially what I want is, because I want a du dt, I want the first order derivative. Let me just rewrite it as just the u prime. Okay, I really want the u term to disappear, right? I don't want my derivative approximation to depend on the actual height of the function. I want my u prime, u double prime term to disappear because I don't want a first order scheme. Also, if I on the third order scheme, I also don't want the second order error term. So I want this also to be 0. Which means that when I multiply this part of the matrix